Welcome to this tutorial session. So here I will be taking upon the tutorial on the topic of on the subject power system engineering. This is the 10th tutorial session, and before I start, I would like to introduce myself. I'm Mohd Owais, Prime Minister Research Fellow, Electrical Engineering Department, Aligarh Muslim University. So we will continue what we have been talking about in the last previous tutorial session about the load frequency control. Load frequency control. So we have already discussed about why we need a frequency control. Why we need a strict limit on the frequency control. I would like to summarize over here why there is a strict limit on the frequency variation we have talked about here. First point is in that under frequency operation will lead to the saturation of transformers which are operating in the power system. Another is that if we operate the fre- if we operate under frequency operation, then or we would say that of frequency at a lower than the normal frequency, and what will happen here is that speed get affected, and it will lead to a damage of the turbines. Okay. Another most important thing is that uh, these subnormal operation, the subnormal frequency operation lead to the uh, lead to the reduction in the load demand. Okay, and it will not able to supply the appropriate load demand. So basically, we have discussed about what are various models, like we have discussed the generator turbine model over there, in which what we have done, we have derived an equation of the a Laplace control equation for this. Now today what we are going to do here is we will actually derive an equation, and after that we will solve various questions. Okay. So let me give you the topic which we are going to discuss today in detail. Just a second. Mm, Okay. So what we are going to hear, uh, we are going to analyze the two area load frequency control. Then after that we will solve questions, because in this questions are very much important. Okay. So let's say there is a let's say there is a extended power system and it has two areas and it is divided into two areas. The control area 1, this is control area 1 and this is control area 2, and it is connected by a tie line which connects these area. Okay. Now the objective here is that how to control the power flow between them, which will eventually control the regulate the frequency. And let's say the power transported out of area. Let's assume power out of area 1 is P, is known as V1, V2. Let's say this has voltage 1, del 1, V2, del 2, and V1, V2, X12 sine del 1 minus del 2. Okay, so what are these del 1? These are the equivalent machine power angle of these two areas. Now, for incremental change for any incremental change in del 1 and del 2, the incremental power can be expressed by how? Which is del p tie, because that incremental power will go through the this tie line. So basically this equation in this which I have wrote this equation, it is also known as tie line power. Okay, this is also known as tie line power. It is equal to change in del 1 minus del 2 multiplied by, let's say, a constant T12. So change incremental tie line power is equal to V1 V2, okay, P1 PR1 X12 del change in del 1 minus change in del 2. This is known as synchronization coefficient. Synchronizing coefficient. Okay, as you can see here, so the incremental are angles are generally know that they are the integrals of a frequency. Okay, change in angle is a function of a incremental frequency. Sorry, integral frequency. So we can say that p tie is equal to, if we convert it into frequency, then integration of change in frequency in the first minus integration of change in frequency in the two with respect to time. And what are these del f1 and del f2? These are these are frequency changes in the area 1 and 2. Okay, and here what is T1, which is a synchronizing coefficient. Okay, for here now with this equation we can say that it is dependent upon the change in frequency. Okay, now and we also know that last time we have discussed it that del Pg minus del Pd is equal to 2h upon f d by dt del f plus b pu b per unit into del f. We have derived this equation for a generator turbine model. So basically this equation, we will be using this equation here, and if we implement this, so what it will come to here is that for here, for area 1, area 1 del Pg will become del Pg1 minus del Pd1 is equal to 2h1 f1 d by dt del f1 plus b1 del f1. Okay, but this incremental power will plus, there is another term here which is the tie line, because the incremental power balance equation for area 1 will be this much. Okay, now if we take the Laplace transform for this, if we take Laplace transform, okay, it will be del Pg1s minus del PD1s equal to 2h1 upon f1 s del fs1 plus b1 b1 del f1s plus del p tie. Okay, which is also an equation of s. Okay, okay, so basically what it will be, if we rearrange for del fs, so that rearrangement will be like this. Del, just a second, let me write it over here. Del PGS minus del PD1S minus del P tie S equal to, on the right side what remains here, 2H1, 2H1 upon F1 S plus B1 S del F. And last time, this equation we have derived into a control loop which is known as Kp upon 1 plus STP, where Kp is equal to 1 by B1 and TPS is equal to 2H1 by B1F. You can go through the last lecture derivation where we have derived this all in a generator turbine model. So basically, it will be, if we rearrange this, S1 will become on 1 upon like this. So in del Fs will become equal to del Pg1s minus del PD1s minus del P tie multiplied by, let me write it, that function here, multiplied by Kp S1 1 plus S TPS. Okay, and obviously KPS is equal to 1 upon TV1 and 1 upon B1, and TPS1 is 2H1 upon B1S. Okay, so if we draw a, a flow graph, or I would say block diagram, so it will be like here, like it is a summation point, a control signal is coming which is of deep del p type for any incremental change, here coming generation for area 1, here coming the demand del P D1 for area 1. This is minus, this is minus, this is plus. Then it goes toward multiplied by this block, which is Kp S1 divided by 1 plus STP S1, and then output is the frequency. So this relates the frequency with last time we have not taken here. We just related with PG1 and PD1. Now this time we have taken another thing where there is an extra power is going out based on that del p tie. Based on this we can calculate the del fs. So it will relate, it will give the control area, control of the how the frequency is controlled for every area. Like if we want to implement it for the area 2, we can use all those values of del pg2, del pd2, kps2, which is b2, 1 by b2, all those things, and it will be for the uh, second area. Okay, so basically this is the frequency control of a 2 area. Okay, a basic one. Now let's move towards some of the questions which I want to discuss with you. This is a very advanced topic. So let me solve it one question. Last time we have solved many questions. I hope those give you a better understanding how we can implement it. Just a second. Let me get. So let's solve one question. Okay. 100 MVA synchronous generator operates on full load at a frequency of 50 Hz. The load is suddenly reduced to 50 megawatt due to time lag in governor system. The steam valve begins to close after zero point 0.4 second. Determine the change in frequency that occur in this time. Okay. So basically, what we have to find here, we have to calculate the change in the frequency. Okay, so let's solve this. Here in the question, it is given. We know that we have seen in the last lecture that kinetic energy is directly proportional to the frequency square. Okay, so what happened here is that a 100 MVA synchronous generator which operates on the full load at a frequency of 50 Hz. Then what happened? Its load is suddenly reduced to 50 megawatt. We have to find the change in frequency. So initially, kinetic energy in this actually H is given 5 kilowatt second per kVA of the generator. Okay, so first is kinetic energy stored in the rotating part of generator and turbine. It is equal to H is given 5 multiplied by MVA 100 into 1000. So it come out to be 5 into 10 raised to the power 5 kilowatt second. Now load is suddenly reduced, so the excess power input to generator before steam valve begins to close. What it is? 50 megawatt. So energy in the rotating part in 0.04 second, how much it will be? So excess energy input in zero point 0.4 second, how much it is? 50 into 1000 into zero point 0.4. So it will be how much? 2000 kilowatt second. As we know that stored kinetic energy is directly proportional to the frequency square, so like energy is directly proportional to frequency square. So E2 upon E1 is equal to F2 upon F1. Okay, so F2 will be equal to E2 upon E1 square into F1. Okay, what is E2? Energy stored after load reduced, which is initially energy stored in the kinetic is this much, then excess energy in the zero point 0.4 second will be this much. So basically we add both. So 50 0 0 0 plus 20,000. E1 here is which is initially. This will correspond to F1 at this time frequency is 50 Hertz, but F2 we have to calculate. So F2 is equal to 50 under root plus divided by, okay, so it will be equal to 3025. So we will calculate F2 is equal to 50, 52 by 50. So let me calculate its value first. Under root 52 divided by 51, sorry, 50. So it comes out to be around 50.99. So value comes out to be 50.99, which we can say that 51 Hertz. Okay. So after the reduction is load is reduced, the frequency will become 51 Hertz. This is the answer to this question. I hope you understood that. Now moving on to what next question. So here in this question it is given two generators which are rated 200 megawatt and 400 megawatt are operating in parallel. The droop characteristics of their governor are 4% and 5% respectively from no load to full load. Assuming the generators are operating at 50 Hertz at no load. Okay, so how would a load of 600 megawatt be shared between them? We have to find the frequency also. What will be the frequency of the system? Okay. Okay. So here we have to find. Now what happened here is that their droop characteristics are different. So basically, they will, you know, share the load in an uneven manner. Like if they have same droop characteristic, they may have shared the load in a equal manner, or I would say in the rated manner. Okay, so let's solve this question first, and then we will discuss about another thing. So let's assume out of 600, let's assume out of 600, generator 1 have a take load of X megawatt. Therefore, generator 2 will take a load of 600 minus X megawatt. It's quite clear. G1 of rated capacity 200 and G2 is a rated capacity of 400. Okay. Let's assume a reduction in frequency is del F. Okay. So for first generator, for first generator, del F upon X equal to 0.004 into 50 divided by 200. Okay, this is, I think, quite clear. So from here, del F upon X will be 1 by 100. I think I have written the right thing. Calculation is correct. Let's say this is equation 1. For second generator, del F upon the change in load is 600 minus X. Droop characteristics of zero point 0.5, 50 frequency, and 400 is the rate. So let's solve this. This will come out to be 250 and it will be 2.5. I think I am correct. Okay, if not, then you can write in the chat box. Okay, cross multiply, we get 400, or let's solve it for del F. So 2.5 upon 400 into 600 minus X. So del F here will be equal to 1500 minus 2.5x upon 400. So let's say this is equation 2. And equation 1, if we rearrange this equation, it is del F is equal to x upon 100. Okay. So x upon 100 equal to 1500 minus 2.5x divided by 400. Okay, so this will cancel out and it will be equal to 4x is equal to 1500 minus 2.5x, and 4x plus 2.5x is equal to 1500. It will be equal to 6.5. x is equal to 1500. So let me calculate its value. So if we calculate x value 1500 divided by 6.5, it's come out to be 230.7, or we would it's, if we round off it, then we can say 231 megawatt. So out of 600, 231 will go towards the generator 1. Then load on generator 2. How much it will be? 600 minus 231. Okay. So 600 minus 231. How much it is? 369. So megawatt. Now you can see here generator. I will write it here. Generator 1, generator 2. Rated capacity. Rated capacity. How much? 200. It's 400. Load कितना है इसमें? It is 231 and it is 369. So you can see here clearly that generator 1 is overloaded. Okay, and generator 2 is underloaded. So it is not a desired, you know, result, because this will always be overloaded. You can see here extra 31 megawatt will be there, and it happens due to the difference in the droop characteristics. Okay, so if we have, let's assume let's assume both have 5% of droop characteristics. Okay, so how what it will be? So let's solve it. For that, for generator 1, del f upon, I know the answer, but I want you to see the answer through the numerical, because there is a direct, if I give you a concept about this, you can directly say how much it will be, but I want you to get through the equation. Okay, let's say it is through the calculation. It is 50 divided by 400. For generator 2, del f upon 600 minus x 0.05 into 50 upon, this is 200. First is 200, second is 400. So let's solve this. So let me solve it first for this one. So it will come out to be 2 del f upon x is equal to 2.5 upon 200. Okay, for generator 2, del f upon 600 minus x 2.5 divided by 400. So if we cross multiply it, 400 del f is equal to how much? It will become out to be 1500 minus 2.5x upon 400. So it will be equal to how much? 2.5 into x upon 200 in the second case, this one. So it will go about 2, and if we multiply it, 1500 minus 2.5x is equal to 5x. It will come out to 7.5. 1500 x is equal to 1500 upon 7.5. 1500 divided by 7.5. So it will be 200. So generator 2 will be 600 minus 200 is equal to 400. So here I would again write G1, G2, rated capacity. Okay, what is the rated capacity? 200, 400. Now here, same group characteristics, same group characteristics, and 4% and 5%. So you can clearly see when it's the same group characteristic, they have 200 and 400 load. This is a load. But if they have different, it will 231 and 369. So what it shows here, it concludes that if we operate the generators in parallel, if their group characteristics are same, then they will uh, uh, then what happens here is that they will demand, the load will be shared based upon their rated capacity. Okay, and if it's different and the demand is the load is higher than the rated capacity, then the lower MW or size generator will get overloaded. You can clearly see here. So this is, and that's why this is a desirable operation. Okay, now another thing in the question is here, we have to find the frequency. So the system frequency equal to 50 minus group characteristics is 0.04 into 50 divided by 200. So it will be equal to how much? Sorry, multiplied by 231. So the system frequency will be, we just calculated from the value, 0.04 into 50 divided by 200 multiplied by 231, and if we minus 2.31, it comes out to be 47.69 hertz. This is the system frequency. Okay, so now let's move on towards the another question. A system consists of four identical 400 MVA generating units feeding a total load of 1016 megawatt. The inertia constant H of each unit is 5.0 second on 400 MV base. The load changes by 1.5% for 1% change in frequency. Okay. When there is a sudden load change, when there is a sudden drop in load by 16 megawatt. Okay, we have to find what we have to find. Obtain the block diagram expressed on 1600 MV base. Okay, so first of all, we will do this. Now, if we refer those on to a base case, then we have to find the H equivalent on a 1600 base MV. Okay, so H equivalent will be how much? 5 into 400 upon base is 1600 and they are in number 4. Okay, they are in 4. H value here is 5. So if we multiply it, all 4 comes out to be 5 seconds and F0 is 50 hertz. Okay, so what is given here in the question is that there is a change of 1% load change for a change in 1% change in the frequency. Okay, so del PL upon del F is equal to how much change in the frequency? How much change in the load? It is 1.5%. But of what? Actually, it is given in the question that when there is sudden drop in load by 16 megawatt from this value. So 1.5% of 1016 minus 16. Okay. Then 1% change of the frequency, which is 50 already. Okay. So if we solve it, it comes out to be 1.5 into 1000 divided by 50. Then change come out to be 3 megawatt per hertz. So for every hertz, there is a change of 30 megawatt. So we can say here D is equal to 30 megawatt per hertz. Okay. Now we know that what is TP? 2H equivalent divided by DFO. So 2 into H5 D we just calculated, it is 30 multiplied by 50. I think just a second. 10 divided by 30 into 50. Okay. Okay, just a second. So this is the value which we have calculated. But if we want in a per unit, then we multiply it by divided by base, which is 1600. So it will come out to be 3 by 160 per unit. Okay, this value we will use here. So it will, how much it will come? I think it's 16 upon 15. 3 by 160, 2 into 5. 10. Just a second, let me. it come out 2 into H equivalent is which is in per unit F, then D is 3 by 160 multiplied by 50. So it will come out to be this much, 2 into 160 divided by 3 into 10, it is 32 by 3. Okay, 32 by 3. Okay, so basically this much will come out. Now here we have to find the block diagram express when actually one thing is missing, when there is no governor action. We have to use that when there is no governor action. So for that, here what we have, no, we have kp which is 1 by d, okay, which is 160 by 3 per unit. Okay, we calculated tp 32 by 3 second. Now we know this block diagram PL, or we can say here PD in our say. This is PG, this is minus, this is plus, and it is multiplied by a block diagram KP plus 1 by STP, and this is del F. We already know how we calculate it. Notations may be different, but that's not a problem. So here, the load change here is, what is del PL? Del PL is minus 16 megawatt. So in per unit, we will calculate in per unit on a base of how much? 1600. So 16 divided by 1600, it comes out to be zero point 0 per unit. Okay, because it is given in the question, we have to calculate on the base of 1600 MVA. So now what happened here is that del PLS is equal to, now for a step decrease, what is given here? The load changes in each one with a sudden drop in a load by 1600. So we will assume it by using a for a step decrease in a load by 0.01. I will write it here. So it will, for a decrease in load by how much? 0.01 per unit, Laplace transform of PL will be del PLS, and it is equal to minus 0.01 S. We know the Laplace transform of step in input is 1 upon S. So from here and from the block diagram, we already know what is del Fs. What is del Fs? Del Fs is equal to Kp 1 plus STP multiplied by change in the this PL. So we have given, okay, so del PL. What is del PL? Minus 0.01 S. What is Kp? Kp is 1 by D. We just use that function value, but let's assume first of all here, just a second. Okay, 1 by S plus 1 by STP. So we have to find, we know that how to calculate this value. Let 1 upon S 1 plus STP is equal to K1 upon S plus K2 upon 1 plus STP. We know how to calculate these K1 and K2. Okay, so K1 1 plus STP plus K2 S divided by S 1 plus STP, and it is equal to 1 upon S 1 plus STP. So this will cancel out. So we would say that K1 plus K1 as Tp plus K2 as equal to 1. Okay. Now, if we compare in the right and left hand side, K1 will come out to be 0, sorry, 1, not 0. We have the value 1, but as function is not here, so K1 Tp plus K2, it will come out to be 0. Okay, and we know what's the value of K1. So K2, how much it will be? K2 will be just a second, minus Tp. Okay, minus Tp. So we found those values. 1 upon s 1 s Tp is equal to how much? 1 upon s minus Tp upon 1 plus s Tp, because in the end we have to calculate the inverse transform also. That's why we are going over this. Okay, so if we put these value in this del fs, what we will get here? Del fs is equal to 0.01. Okay, 0.01, 1 upon s minus Tp by 1 plus s Tp. Okay, so here this 0.01, if we take the inverse Laplace transform, 1 upon s, it will be minus 1, and this will be e minus t by Tp. Okay, how we can take Tp common? It will come out to be, just a second, let me do one thing here. Tp here, Tp here, just not directly writing it. I will write it over like this. Okay, this is del fs. Oh, okay. Here it is K1, K2. We just get okay. One thing is missing. Okay, KP. KP is missing over here. Okay, I think it is correct. Okay, now 0.01, 1 by s minus. If we can take STP common, sorry, TP common, then 1 s plus 1 by Tp will be here and Kp will be here. Okay, I hope it is understandable right now. Okay, so del ft, it will be 0.01, if we it is Kp minus 0.01 Kp e raised to the power minus t by Tp. Okay, we know the Laplace transform of this function. It's quite explanatory. And what is Kp? What is Kp? Kp we have to see. Kp is 1 by d. And what is d? It is 3 by 160. So here, putting that value, we will get how the value of this 0.01 into Kp, which is 160 by 3, minus 0.01 Kp, which is 160 by 3, into e raised to the power t by Tp. And Tp value is, just a second, let me see what Tp value is. Tp value is 32 by 3. It is 32 by 3. So if I rearrange this, del ft is equal to 0.01 into 160 by 3 minus 0.01 into 160 into 160 by 3 e raised to the power 32 by 3. Okay, and if we can solve it further, It's quite easy. It will be 1.6 by 3, I think. 1 minus e raised to the power 3t by 32. Okay, this is the frequency. Okay, and if we want to get the steady state frequency, then we can say the limit t tends to infinity del ft. And if we calculate it, it will come out to be, this will go become 0, 1.6 by 3. So it will come out to be 0.533 hertz. So what it will be, I will here draw. This is the frequency. At the steady state, it will come out to be like this. This is the change in frequency versus time. This value is 0.533. Okay, so the change in frequency versus time graph will be like this at the steady state. Okay, so this is how you solve these type of questions, and basically this block diagram is very much important for this, for the calculation of. I hope you understood that. Now let's move on towards some other questions. Okay, for modeling of a typical three-phase balanced power system, the time constant of the speed governor TSG turbine T1 and power system TPS have to be chosen from given time constant. Which one? Which one will sufficiently accurate choice for TSG. तो टाइम कॉन्स्टेंट्स क्या है? पहला टाइम कांस्टेंट है 0.65 सेकेंड, दूसरा है 0.45 सेकेंड, तीसरा है 25 सेकेंड और डी है 0.005 सेकेंड। तो इसमें से बताना है कि कौन सा चॉइस ऑफ टाइम कांस्टेंट will be accurate for a accurate for the speed governor. Okay, give me the answer. So what happens here is that for a typical power system, for a typical power system, time constant of power system is always greater than the time constants of turbine, which is always greater than the time constant of speed governor. ओके, सो क्या कह सकते हैं कि स्पीड गवर्नर का सबसे कम होगा. So let's say which have the lowest value. So D as the lowest value. So sufficiently accurate will be the D1. Okay. So another question. The main objective of AGC is to first maintain frequency alone, B maintain the correct power exchange, C optimize the economical value of generation, D all of the above. Give me the answer. So EGC का काम होता है, it has to maintain the frequency, maintain the correct power exchange and optimize the economics. So we can see all of the above. Now another question. is a power system has two synchronous generators. The governor turbine characteristics corresponding to these generators P1 is equal to 150 60 minus F and P2 is equal to 75 60 minus F. Okay. F denotes the frequency in hertz. P1 and P2 power output 1 and 2. Assume these are lossless operation. If the total load supplied by generators is 1 megawatt, find no load frequency at generator 2. Okay. Also calculate the percentage load shared by the generator 1. Find percentage load shared by generator 1. We have to find this. So क्या है कि characteristics दी गई हैं of generators. पहले जनरेटर की characteristics क्या है? P1 is equal to 150 60 minus F and P2 is equal to 75 60 minus F is equal. Now we have to find the no load. So basically for no load frequency, let's put this equal to 0 and then it will come out to be 60 minus F NL is equal to 0. So F NL is equal to 60 Hertz. Okay. So the no load frequency will be this much. And for and these all supply P1 plus P2 supply 1 megawatt, which is 1000 kilowatt. So 100 just no, 150 150 60 minus F plus 75 60 minus F is equal to 1000. So 150 multiplied by 60, it will come out to be, I think this is the, if we expand this, it will come out this much. So 150 plus 75, it will be 225. So 9000 plus 4500 minus 1000 is equal to 225f. This will come out to be 225f, and f is equal to, if we multiply it, how much will value is, f come out to be 55.5 hertz. So at the full load, the frequency will be this much. Now at this frequency f, when f is equal to 55.55 hertz, then P1 is equal to how much? 150. 60 minus 55.55. We know that they are all governed by this equation. So 60 minus 55.55 into 150. So the load output will be 66.75 kilowatt. Similarly, for P2, its value is 75. 60 minus 55.55. So 4.5 into this. So if we calculate it, you can, it is 337.5 kilowatts. And you can see that if we add these both, 337.5 plus 667.5, it will come out to be, just a second, there is some mistake in calculation. This is 33. Okay. So if we add these both, it will come out to be 1000. Okay. So percentage load shared by generator 1 is equal to how much? Generator 1, this 667.5 divided by 1000 into 100, so it will be 66.75 percentage. Similarly, percentage load shared by generator 2 will be 33.35%. This is the similar answer. I hope you have understood this problem. Okay. So another question, which is very interesting one. I think you now you can solve these questions because we have spent a lot of time on derivation of various questions, various formulas, and those formulas are directly applied over here. A 25 MVA 50 Hz turbo alternator. It operates at full load at unity power factor. A load of 1.25 megawatt is suddenly applied, and the steam valve applied to the machine, and steam valves to the turbine commences after zero point 0.5 second due to time lag. in the governor. Assuming constant H is equal to 3.2 kilowatt second per kVA, and the generational capacity. Calculate the frequency. What we have to do? We have to calculate the frequency just before the steam valve begins to open. We have to calculate that frequency. So, okay. So here, let's solve this. This is based upon the same, you know, the thing which we have just solved it. Okay. What we know here, we know del F T. It is del PL into Kp 1 minus Et by Tp. Okay. This is the, and what is Kp? Kp is 1 by D. And we know that at steady state, what is frequency? It is del PL into Kp. We just calculated here in the previous equations, like I'll show you here. This is the, this is all we just calculated. So using that information, we can use this. So here what we have to find, it will be del PL into 1 upon D. So what we have to find? D. And we also calculated D. What is D? It is del change in demand with respect to frequency. So what is given here in the question about the change in the demand? So demand changes 1.25 megawatt. So it is, just a second. We just like here, we will calculate the, I will show you how we are going to calculate that, because this all calculation we have already done in our lecture. I will show you just a second. Okay, here, see, it is change in the demand multiplied by the percentage change in the frequency power. Okay, so here, let me see in the question, there is something missing. That's the problem. Okay, just a second. Let me see. There is some problem in this question. Let me see. Okay. So basically, we have to find the del PD. Okay. So the change in is applied to the a load. Okay. How much load is applied? 1.25. Okay. This is the change in the load divided by the change in frequency, and it is not given here. Okay, just a second. Let me see. Okay, yes. So del F is here zero point 0.5 into 50 because the time for that is the turbine commences to the operation after zero point 0.5 second. So therefore del F will be zero point 0.5 into 50. So let me solve it for you. It will come out to be how much? It will come out to be 1.25 divided by 250, so it will be 25. Okay, let me calculate it. Zero point 0.5 into 50 divided by 25. Okay, so let its value comes out to be 0.05 megawatt per hertz. Okay, this is the value of D. And load change, we already know here. How much load changes suddenly? 25. This. Okay, load change here is which is del P. Del F is equal to how much? Del P. It is 1.25 multiplied by D, which is 1 by 0.05. Based on that, we can calculate. Actually, some of the things I assume in this question is missing. That's why we are not able to get the correct answer. Let me see one more time. This is correct, okay? Okay, let me see again. Yeah, there is something missing. Hmm. Let me see just a second. Just a second. Okay, let's leave this question. I think some data is missing in this. That's why we are not able to get it correctly. Okay. But on the methods to step to the solution is this. Like we do first of all, calculate if we have to find the steady state, like how we calculate. So we will use this equation del PL upon 1 upon D, and we know then how we calculate D. So let me give you another question where the data is correctly given. Okay, yes. Here. Mhm. A 50 hertz small system small system consists of five identical 300 kVA generating unit. feeding a total of 125 kilowatt. Okay. Inertia constant is 2.5 on 300 kVA base. This is important. Now, here the load varies. Load how much? 1% for 0.5% change in frequency. Okay. If there is a sudden decrease in load of 150 kilowatt, what it is here? It is a sudden decrease in load. Sudden decrease in load. Okay. Find the steady state. Now we have to find the steady state. So basically, with what we will use this equation to calculate the steady state frequency change. Okay. So now, but here is a catch. The, the 5 identical is given on 300 kVA. Okay. 2.5 on the 300 kVA base. So basically, first we will calculate dPd divided by dF. Okay. So load varies by 1%. Like what we have calculated over here, like in the previous questions, I will take you back toward that. Okay, here, what here it is 1.5% for 1 percentage change. Okay, so in the load, and load changes to 16 megawatt. So basically, what we will do here, uh, the change in load is 1 percentage, and for 1250 to 150. So change in load is this much, and zero point 0.4 into 50. So it will come out to be 0.00111 upon 22. So I think it is correct. So let me solve it for you. 1100 divided by 2, it will be 550. Okay, megawatt hertz. Now if we divide it by uh, okay, this much, if we divide it by 300, so here, because if we calculate in a per unit, then we can also go toward 550 divided by 300, come out to be 1.833. Okay, so del F is equal to P is given 1 percentage. What is the del PL? In the previous question, like we calculated the del PL here, just like here. In that question, what is given here? We calculated the del PL here. This just a second, where we calculated 16 megawatt. But in this, the base is remaining the same on the same base. So we will convert into del P, which is how much it is given. It is total load 150. 150 divided by 300, it will come out to be zero point 0.2, okay, per unit megawatt. So zero point 0.2 multiplied by 1.833. So if we calculate it, value 1, just a second, zero point 0.2 divided by 1 point, it come out to be 0.109. So change in frequency will be this much. And if we minus it from 0.0109, so it will come out to be F is equal to F naught plus del F, and this del F will be minus. So because there is a reduction in the load, so it will be 0.109. It will come out to be, I think, 50 minus 0.109, it come out to be 49.89 hertz. So this will be the frequency at this time. Okay, so you get an idea how we are going to solve these questions. If someone asks, we will first calculate the D if for the steady state, because generally I don't think other than steady state the questions will be asked. It will be up to the steady state. If someone wants to derive, for that I have also solved your question how to derive a block diagram or equation. Okay, here in this, based on this we have derived it. Okay, now, okay, let's I think if there anything missing or any questions we can, if you have any question you can ask here. Okay, if you have any confusion regarding the solution you can ask in here. Okay, write in the chat box, I'm waiting for that. Otherwise, let me see if I can get any question for you. Basically, generally, I have already covered all those questions which can be, asked over the load frequency controls. So solve those all those questions. If you have any specific question or any doubt about these, we can discuss that here. Okay. So okay. So I think everyone have understood this thing. So with this, I will end today's session. If I think no one has any doubt regarding the numericals, so we will end today's session right now. And if you in a next week, if you find any doubt, you can ask me in the next week. We will meet again. Okay. Till then, goodbye. Thank you for all you joining.